Okay, so we've been talking chapter two, and we got into last time sort of significant figures, and we also got into conversions and equalities. So remember, as we talked about, equalities are really two values that are on different scales, but they do represent the same amount of something. Again, like 12 inches equals 1 foot. 1 inch is 2.54 centimeters. 1 mile is 5,280 feet. So from any equality, as we talked about, you really could write two conversion factors. And conversion factors, again, are really just fractions, where, for example, you put one over on top and the other unit on the bottom, or you could flip it around and kind of do in the opposite direction. And really, the purpose of the conversion factors is really how we show our work here in chemistry and how we do want to set up all of our problems, as we talked about at the end there, which is dimensional analysis. And a dimensional analysis is where we do use conversion factors and we use a setup where basically opposites cancel the units. And we want to do that to get our answer that we need. So, for example, if we were going 32 miles and we want to know how many feet that was, we would set it up like so, 32 miles. Again, miles are up on top. And again, if it helps you or if you need to, you can put a 1 over it. But again, that's up on top. So we want to get rid of miles. So it makes our decision making pretty straightforward there. We're going to choose the one where miles is in the opposite location. And what's going to happen here, always when we do dimensional analysis, is we multiply the top and we divide the bottom. So whatever's on the top gets multiplied, what's over on the bottom gets divided. And in this particular case, we go 32 times 5280. That's going to get us 168960 feet. And essentially what's happening here in terms of the units is we have miles up on top. We have miles on the bottom. We're basically dividing them by themselves. They become one, and essentially the units cancel out in this case. That leaves us the only unit we have left, which is feet. And remember as well, when we kind of look at it, we're looking for significant figures always when we set it up this way, because all we're doing is multiplying or dividing. So in this case, we wouldn't worry about this one as it's considered an exact number. We would look at this one, which is 2, and we actually would go to here and perhaps a 17, 1, 2, 3, 4. I think we got it right. 1, 2, 3, 4. Feet would be where we might want to end up, or we could use scientific notation if we wanted to as well. But again, you do need to get in the habit of kind of setting up your problems like they're on the bottom, as again, that's usually what they mean when they say show your work. They want you to show it that way. It cannot just be sort of random numbers all over the page and stuff like that. So it's got to be set up like this, that you can see the units canceling out. Any questions on that there? So one of the things that we did talk about again is you really don't have to worry about any type of conversion that you use that's considered an exact number. And for sure, that's metric to metric type conversions. English to English conversions are a couple of those that cross over, like 1 inch is 2.54 centimeters. You do have to take those guys into consideration if it is a metric to English crossover. That's not one of those couple that we talked about that are sort of exact. And remember, if you're going to have to take those guys into account, you do want to look at the actual number there, not the one that's a 1 usually. So you want to look at the actual number in terms of sig figs. The other things that you usually do need to take into account, as we talked about, is if you have some type of conversion that's sort of given to you in the problem that's kind of specific for the problem. It's not like a true conversion, if you will. That's something else that you would look at. All right, so I think that's where we left off. So I don't think we did any examples. So we'll just look at this one real quick here, just to reiterate the point. In this case, we want to know how many pennies there are in $3. Obviously, what you would want to choose is a pathway to get you there. And since there's 100 pennies in $1, that gives us our two possible conversion factors. So on this pretty straightforward one here, we're going to start with what was given, which is our dollars. Once again, it is on top, which means we would need, obviously, dollars in the opposite location here. Again, we're going to multiply there and divide what's on the bottom, and that's going to give us 300 pennies. In this particular case, again, we would not worry about this one. This is really the only number that we have in the problem, so one significant figure would work here. So we would not want to, for example, put a decimal point at the end of it. Otherwise, we would have three significant figures, and one would work here. Again, the units here are going to cancel, basically. If you are solving for one unit, typically speaking, that one unit should be on the top and the only thing left. If you are solving for two units, so you need to make sure the units end up in the right location, top or bottom, wherever they need to be, um, as you go through it. So once you try one here, let's say we go to the local AM/PM, we got a 32 fluid ounce drink of Diet Coke. How many gallons did you drink? So I'll give you some equalities here that might help you get there. And obviously our conversion factors that go with those. All right, so set it up using dimensional analysis and get the answer. So take a few moments. Okay, so let's take a look. Again, you want to think about when you're doing a conversion problem, sort of where you're starting and where you want to end, and a pathway to sort of get you there. So in this case, one pathway was we could go from fluid ounces to quarts and quarts to gallons to kind of get us there. Again, you want to find some equalities that will get you there, and obviously the conversion factors there. We're going to start with what was given, which is 32 fluid ounces. Again, that is on top, so we want in the opposite location the fluid ounces. So that one right there would do it for us. 1 quart, 32 fluid ounces. Once again, here we're multiplying what's on top, we're dividing what's on the bottom, so that is what's going to get rid of those units. If we stopped right at this point, we're in units of quarts, which is not where we want to end up. But because we did set it up this way, we could clearly see, hopefully, that quarts are up on top, which makes our decision for our final sort of conversion pretty easy. Since quarts are on top, opposites cancel. This is the proper conversion factor I need to use to do that. We could just continue on as well. We don't necessarily need to get an answer. If you did get an answer, you probably shouldn't round too much or anything like that. In this case, it'll just be one, but we'll go with 4 quarts and 1 gallon on top. Once again, we are multiplying and dividing this. Again, that division is going to get rid of the quarts. That's going to leave us the only unit left, which is what we're actually looking for. So essentially, in this case, we're taking 32 times 1 times 1, hit equals, divided by 32, and divided by 4 gets us 0.25 gallons. In terms of significant figures, we really don't have to worry about too much here, except for the original one that had 2. So we would take it to 2 significant figures. That is the proper answer, by the way. It is not 1/4. You should not leave an answer in a fraction. You should divide it out. Just makes me think you're too lazy to do it. Yeah, so make sure you divide it out. Don't leave an answer as a fraction. Definitely get some type of answer to the proper number of significant figures. Any questions on that one there? All right, let's continue on then. Why don't we try this one? An antibiotic dose of 500 milligrams is ordered. If the antibiotic is supplied in a liquid form as 250 milligrams in 5 milliliters, how many milliliters was given? So take a moment there and see what you come up with here. Maybe some information might be helpful. Yeah, I'm sorry. Yes, yeah. Oh, are you talking about the conversions and all that? Yeah, so what you need to show is really the final setup there with the dimensional analysis. If it helps you to show the conversion factors, you can, the given and all that. You don't necessarily have to show all that. So for example, that one we just did on the previous slide there. Really for credit, full credit, that's what you need to show on the bottom there with the setup like that and the answer to the proper number of significant figures. You don't necessarily have to show any of that unless you want to help yourself. But for credit, you need to really show what's kind of on the bottom there, the dimensional analysis setup and all that. So let's take a look at this one. Again, we have 500 milligrams. And in this particular case, we actually have a conversion factor sort of given to us in the problem. And that is a conversion factor that, again, we could use like it was sort of written there, or we can flip it around and use it in this direction. Here, again, we're going to start with the 500 milligrams. That is up on top, which means opposite's going to cancel. So we actually do want to use it in this form. And if we do that, we are going to end up with 10 milligrams. We're going to cancel here, and milliliters would be left over. In this particular case, because this conversion factor did come from the actual problem, we do need to kind of look at the significant figures in that conversion factor. So, for example, this guy would have 2 significant figures. This guy would have 2 significant figures, and this guy would have 3 significant figures, which again means because we are multiplying basically and dividing, we are looking at smallest sig figs, which is 2. That means we actually do need to put something like a decimal point there to get us to 2 significant figures in this case. Again, if we left it like I had it originally written, it would have obviously just 1 significant figure there, the 1 in that case. Question on that there. So that's the other situation where you should really kind of look at the significant figures and a conversion factor if it's, again, pretty much provided to you in the problem. Obviously, all medications are not provided like this, 250 and 5 milliliters, so that's specific to this sort of problem, and you should look at the significant figures associated with it. Any questions on that there? And once again, as to the earlier question, for full credit down here, that's what you need to show to get full credit. Again, if it helps you to do all the other parts, do the other parts. All right, let's try this one. During surgery, a patient receives 5 pints of plasma. How many milliliters of plasma were given? There's a couple of qualities that might be helpful. Okay, so let's take a look. In this case, we're starting with pints, and eventually we want to get to milliliters. So again, in this case, we can find a pathway to get us there, go from pints to quarts, and again, quarts to milliliters. That's going to give us those 2 equalities, which obviously will give us these conversion factors that we could use. Once again, we're going to start with what's given to us, which is 5 pints. That is basically on top of the pints. So once again, decision making pretty easy, opposite where the unit needs to go. So the pints are on the bottom and quarts are on top. Once again, multiplying the top, dividing the bottom, that division will get rid of the 2 units there. And again, we are left with, if we stop right at this point, units of quarts. But we do want to get to milliliters. So once again, by setting it up like this, we could clearly see quarts are up on top. So to get rid of them, opposite location, we would want to use the conversion factor here on the right. And again, we're going to put our quarts on the bottom and our milliliters up on top. Once again, we are still multiplying the top and then dividing the bottom. That's going to get rid of the quarts. Going to leave us with milliliters. It'd be good if I put the number there as well, 946 milliliters up on top. So here we're going to multiply basically 5 times 946. We're going to hit equals. We're going to divide it by 2 and hit equals. And that's going to give us on our calculator here 2365 milliliters. Now, when we look at our conversions here, we do need to look at the conversion factor here, as that is a metric to English conversion. So once again, we're going to be looking at the actual 946. So I guess it's good I wrote it. That would be 3 significant figures. This one we don't need to worry about. We also need to worry about this guy, which is two significant figures. So really our answer here should end up with two significant figures. Remember, again, you're doing dimensional analysis, which means the only math you're doing is multiplying and dividing. So you're always going to be looking at significant figures. So we could go 2,400 milliliters. Once again, no decimal. You could also do a little scientific notation, 2.4 times 10 to the 3 milliliters if you wanted to do that as well. Any questions on that there? So again, if you do come across that kind of metric to English, you do have to take it into account like we did here. Not the one that is a 1, but we take into account the one that's actually a number. Any questions on that calculation there? All right, let's try this one. You are stranded 125 miles away from home. You have no money. You decide to walk. If you walk an average of 55 feet per minute, how many days would it take you to get home? So see what you come up with on this one. One mile is, again, 5,280 feet. Problem, we have 125 miles. We eventually want to get to how many days? So what's going to actually help us get there is a conversion factor that's in the problem, and that is feet per minute. And that's basically the rate. So that's going to turn our distance into a time. And from there, we could get to there. So that's actually the thing that's going to kind of help us get there is the standard conversion factor from the problem. The problem we do have, though, is our conversion factor there is in feet in terms of the length measurement. This one is in miles. So we do have to do a conversion to get them into the same unit so we can use them together. It doesn't really matter in a sense which one you want to kind of convert, but you do need to get them either both into feet or both into miles so you can use them together. I'm going to choose to go miles into feet, so I'm going to take the 125 miles to begin with, and I'm going to use the conversion factor, this equality here, to convert it. Again, miles are on top, so I need to go opposite location there and put the mile on the bottom, the 5,280 feet up on top. Here again, when we multiply and then divide, we will be left with feet in this case, and that's going to get me 125 times 5,280 here. That's going to go 660,000 feet. Now that I have my length in feet, I could definitely use this as a conversion factor. And again, we could use it like I wrote it there originally. Or I could flip it around and put the minutes up on top and the 55.0 feet on the bottom. And that actually is the way I'm going to actually need it here because now I'm starting with feet on top. So I do need feet in the opposite location. So I do need to flip that around. And that right there is what's going to take me from sort of distance or length into a unit of time as I multiply here and divide here. The feet are going to cancel. And now I'm in units of minutes. I do need to get to days though. So once again, we could use some conversion factors to do that. I could get an answer at this point, or I could continue on with my work. Again, setting it up like this, I can see minutes are up on top. So once again, I can go opposite on the bottom. So the 60 minutes needs to go in the opposite location. The hour will go up on top. Once again, as I multiply and divide coming through here, the division is going to get rid of both of those. And now I'm in hours. If I was to stop the calculation close to what I want, need to get myself to days. So I could use this equality to do that. Remember that there are only 24 hours in a day, not 60. So here again, we're going to go opposite. So hours on top, hours would have to go on the bottom, and days would go up on top there. Here we would get rid of that. And at this point, again, we are still multiplying and dividing. So in this case, I can take my 660,000. There's really not much to multiply up on top since they're all ones. I'm going to divide it by the first number on the bottom, 55, and hit equals. I'm going to divide it by the next number on the bottom, 60, and hit equals, and divide it by the last number on the bottom and hit equals 24. And that is going to get me some 8.333, a whole bunch of threes and days, right? First off, any questions on the setup here? Now we do need to kind of look at sort of significant figures and where we want to end up. That's an exact, so we don't have to worry about it. That's an exact, which means we don't need to worry about it. Here we do need to worry about, as again, that is sort of a conversion factor from the problem itself. Technically speaking, three significant figures off the 55.0. Now, we do need to look at this number, but this number originally came from that number right about there, which also has three significant figures, because technically speaking, even though I did not round here or anything like that or write in scientific notation, technically speaking, this guy on that conversion should also have three significant figures. So it does look like we should actually end up with, in this case, three significant figures of 8.33 days. Any questions on that? So again, as we talked about previously, you do need to obviously show the setup there. It's a dimensional analysis and the units canceling for full credit. Any questions on that there? All right, so why don't we try just a couple other ones here. Let's do 3,255 cubic centimeters to cubic feet. Yeah. So 1 inch is 2.54 centimeters. And why don't you also do why don't you do 76.5 miles per hour and convert it to kilometers per second. All right, so take a few moments there and do those conversions. See what you get there. Okay, so let's take a look. So on the first one here, we're going from cubic centimeters to cubic feet. So a pathway I sort of chose here is cubic centimeters. I can take that to inches cubed and then to feet cubed, basically. And that means I'm going to start here with my number 3255 cubic centimeters. I could use a regular conversion of inches to centimeters. So we could go 2.54 centimeters is 1 inch. Because this is cubic centimeters, in reality, I have to do it not once, not twice, but technically speaking, I do need to do this conversion 3 times. And when I do this conversion 3 times, centimeters times centimeters times centimeters is cubic centimeters, which will cancel out the cubic centimeters I have on top. Once again, we are multiplying on top, dividing on the bottom. I now have inches on top times inches times inches. Technically speaking, I have inches cubed up on top. Now, I could go from inches to feet using the regular inches to feet conversion, which is 12 inches is 1 foot. Just like I did with the centimeters there, I technically also need to do this one 3 times. 12 inches is 1 foot. Again, inches in opposite locations. 12 inches is 1 foot. Maybe I'll squeeze it in there. 12 inches is 1 foot. Once again, inches times inches times inches gives me inches cubed on the bottom, which will cancel out my inches cubed up there on top. Now, when I multiply the top, I have feet times feet times feet, which is cubic feet. Now I could actually do the math here. We're going to multiply once again everything on top, which is nothing but ones. So we're good on that, I think. 3255. We're going to divide by 2.54, hit equals. Divide by 2.54, hit equals. Divide by 2.54, hit equals. Divide by 12, hit equals. Divide by 12, hit equals. And divide by 12, hit equals. We end up with 0.1149 492 feet cubed. In terms of what we're looking at in terms of significant figures, these are exact, so we don't have to worry about it. Remember, the 1 inch is 2.54 centimeters is also an exact, so we don't have to worry about it. So really, it's this number, which is 4. And I actually did stop exactly at 4, which I guess was good. And we would end up with this one. Questions on that? Yeah. You do not. So what I was actually just going to say is if you wanted to, you could do this 1 inch, 2.54 centimeters, and do a cube on it. It's perfectly fine. The only thing I would say is a lot of times when people do that, they never live to actually do the cubing of the number. They just do like the 2.541. So it's perfectly fine. It's a good way to do it, but very common. People will never live to touch the number 3 times and actually do that math correctly. So if you write it out like that, make sure you do the math correctly. This way, if you write it out the other way, at least you see the numbers 3 times and remember I should probably punch it in 3 times. But again, it's a very common error that sometimes people make is they write it like that and just kind of do the units, but never the number. So yeah, but otherwise it is perfectly fine. So obviously you could have set it up just like this. And again, you would have to remember to do both of those 3 times, but it's okay. Absolutely. Yeah. Other questions on that? All right, on this one, we have miles per hour to kilometers per second. We basically have 2 units we got to convert. We got to take the top to kilometers and the bottom basically to seconds. So what we want to do is, again, use dimensional analysis to our benefit. We want to set it up so we can clearly see where all the units are. So I'm going to start with the miles part first. So I'm just going to use my equality here to do my conversion factor. And again, I can see by setting it up like this, miles are up on top. That means miles need to go on the bottom. So 0.621 miles. Up on top is going to go 1 kilometer. Again, as I multiply and divide here, the miles on top and the miles on the bottom are going to cancel. That means, frankly, if I stop the calculation right at this point, I'm in kilometers per hour, right? So I'm like halfway there. I got kilometers, good. So now what I need to do is take my hours to seconds. Now, by setting it up like that, you should hopefully clearly see hours are on the bottom. So we do need to go hours up on top. And however you want to do this, you could do hours directly to seconds, 3,600 seconds, or you could do hours to minutes if you like. So you go 60 minutes. Hours on top will cancel out the hours on the bottom. At this point, I would be at kilometers per minute. Again, minutes are at the bottom. In 1 minute is 60 seconds. Again, minutes on top and minutes on the bottom would cancel. Now I'm in kilometers per second. And again, we're going to multiply what's on top, which is basically 76.5. They're all ones. We're going to divide by the first number on the bottom, 0.621, hit equals. Divide by the next number, 60, hit equals, and divide by the next number, and which is 60, and hit equals. And that will give us our answer here. And in this particular case, it looks like we're going to go point 0.0342. We do have 2 units. The number always stays with the top unit. The bottom unit is assumed to be 1. So 0.0342 kilometers per second. In terms of significant figures, exact number, don't have to worry about it. Exact number, don't have to worry about it. Here we do have to worry because that is a metric to English conversion. So we look at that number, which is 3. Our original number also happened to have 3. So 3 sig figs there when we're all said and done. Any questions on conversions or use conversion factors? So again, common mistakes people make on these two types of conversions, like the first one we talked about, they don't do it 3 times. For example, bottom one, super common. People do not set it up with dimensional analysis, which you're supposed to do. And at the end, when they get to something like the hours part of it, they're not sure if they should multiply or divide. A lot of people will do this problem and multiply the 60 and the 60 or the 3600. So again, if you set it up dimensional analysis, which you're supposed to, it makes it very simple. It's like opposites cancel, top, bottom. You know exactly where to put the unit you want to get rid of. Any questions on any of that there? All right, the next thing we're going to talk about is density. Density is defined as the amount of matter present in a given volume of a substance. The differences in density, for example, determine whether or not an object will sink or float. If we take water, for example, if an object is more dense than water, it will sink. If an object is less dense than water, it will actually float. For the most part, things in their solid state are typically more dense than in their liquid state because they all lose a lot of energy and they come together really tight and closely packed together. One notable exception to that is actually water. Water in its solid state is actually less dense than in its liquid state. As we know, water in a solid state is ice, right? And when we put ice in our drink, it ends up at the top, right? Because it floats. And that's because when water comes together, because of the bonding it has with other waters, it actually cannot get super close to one another. It doesn't have enough energy to really drop in there and get close. It creates a lot of really open space between the different water molecules and results in a lower density that occurs. The formula for density is mass divided by volume, which obviously you do need to know. Let's come back. There you go. So D is equal to M over V. That means that volume would equal mass divided by density, multiply volume to both sides and divide by density. Mass would equal volume times density. Sometimes people remember this with the DMV triangle. All right. So density is mass divided by volume, volume is mass divided by density, and mass is density times volume there. And the typical units associated with density, as we see on the bottom there, are grams per milliliter, are grams per cubic centimeter, and that's usually for solids and liquids. Remember as well, as we talked about earlier, 1 milliliter is the same as a cubic centimeter. So numerically, those values would be the same. The units would be different, but the essentially would be the same. We don't deal too much with it in this class, but when you get to 1A, you will. When we deal with gases and density of gases, the units typically are grams per liter. But for the most part in this class, most of the time density is usually grams per milliliter, grams per cubic centimeter. But when we do deal with gases, sometimes it's given in grams per liter. All right, so I'm going to try one here. A block has a volume of 25.3 cubic centimeters. It has a mass of 21.7 grams. What is the density of our block here? So take a moment or two and calculate that up. Okay, so in this case, obviously we have a cubic centimeter, which is a volume. We have a mass that's 21.7, and obviously here density is mass divided by volume. So we really have both of those guys actually in the units that we need. So we can just plug and chug into here, 21.7 grams divided by 25.3 cubic centimeters. That is going to get us here 21.7, 25.3. Looks like 0.858. Again, here, none of the units cancel. So again, the number stays with the top unit. The bottom unit is basically 1. So 0.858 grams per cubic centimeter. Again, we are dividing here. So top number has 3 significant figures. Bottom number has 3 significant figures. So again, our answer here should also have 3 significant figures in this case. Any questions on that one there? Okay. Now, when we talk about density and volume, there's kind of 3 ways. For example, we could kind of get the volume. Obviously, one common way we could do that is just simply take a volume reading, right? So we could fill the liquid up in something and take a reading. If we have some type of cube, we could do, like we talked about, length times width times height and do some type of measuring, maybe with a ruler. And again, if they're all in centimeters, we could get our volume here in something like cubic centimeters. So a third way that we could get the volume of a object, usually a solid object, which is very common, especially with density, is what is known as volume by displacement. And volume by displacement means that we essentially put an object in water, and when that object, solid object, goes into something like water or a liquid, it will displace a volume that's equal to its own volume. So for example, if we took something, in a graduated cylinder like you're going to do today, and you had a initial sort of volume, you take a solid and drop it in, what will happen is that liquid level should rise with the solid in there, and that would give you a final volume reading. And basically, the difference between those two volumes would be the volume of the object, would be our final volume minus our initial volume. So same idea here. Before she jumps in, the water's at an initial level. Once she goes in, which would be a solid object, the water rises to a final level. Again, if we take the difference in those two, that would give us the volume of the person that just dove in there and our object in here. So that's a very common way to sort of figure out the volume of a solid object is volume by displacement. Again, the solid will displace a volume equal to its own. So why don't we try one? A student fills a graduated cylinder to 25 milliliters with a liquid. She then puts a solid in the liquid. The volume rises to 33.9 milliliters. The mass of the solid is 63.5. What is the density? We basically have like a graduated cylinder. It's got some liquid in there. It's our initial volume of 25 milliliters. She's going to take this solid, which has a mass of 63.5 grams. She's going to drop it in there. Again, we should expect the volume there to rise, and it does, to a final volume of 33.9 milliliters with the object in there. So once again, we're looking for the density, which is mass divided by volume. We obviously have the mass. The volume here, again, is by displacement, so it is the difference between the two volume levels here. So the volume of our object here is going to be our final volume minus our initial volume. So this would be 33.9 milliliters minus 25 milliliters. And that's going to get you, looks like 8.9 milliliters. That would be the object there's volume, and now we have the volume that we need, and we have the mass, so we could go, our density is 63.5 grams divided by 8.9 milliliters in this case. So 63.5 divided by 8.9, going to get us a 7.1. Once again, the units do not cancel, so grams per milliliter in this particular case. First off, any questions on the calculation there? Now, in terms of significant figures, it is really based off of this calculation here. We subtracted, which means we go to decimal places, 1 decimal place, 1 decimal place. So we took it to 1 decimal place. Although that has 1 decimal place, it does have 2 significant figures, which is important for the last part of the calculation, where we took 3 significant figures divided by 2 significant figures. And that is why we should end up with two significant figures here on our answer. Any questions on that? So again, as we talked about previously, it's important to keep track of like your sig figs and everything throughout your calculation. Although the last calculation you do sort of determines where you end up, some of the previous calculations will have an effect on where you end up on that last calculation. Any questions on that there? Here's density from your book of some objects. You do need to know, obviously, for the most part, the density of liquid water is 1 gram per milliliter or 1 gram per cubic centimeter. So that's something you should know. As we talked about previously there, again, something like ice actually is less dense than liquid water. By the way, density does change with temperature. So density is affected by temperature, and it does change with temperature. But pretty much if you ever need like the density of water, usually in any type of chemistry type problem, and it's not like given to you or anything like that, 1 gram per milliliter is typically a good number to use, and that's usually the number that you would use. So sometimes along your way in chemistry, you'll come across a problem where you like need a density of water. And again, that 1 gram per milliliter is usually the one that you want to use there. Um, so as I mentioned before, what happens with water molecules when they come together in the solid phase is it creates a lot of open space between them. And what that does is essentially bloats ice. And if you think about density, which is mass divided by volume, because it has a lot more of this open space between the water molecules, the volume actually gets larger. And that's why the density of ice actually gets smaller than in the liquid state. Oddly, in the liquid state, the water molecules have enough energy to actually get a lot closer to each other than they do when they have less energy in the solid state, and creates these kind of open spaces between them. So again, water is kind of an unusual substance in that sense. Like I said before, most of the time, solid is more dense. All right, one last one here. Perhaps a student needs 150 cubic centimeters of salt for an experiment. The density of the salt is 2.1 grams per cubic centimeter. How many 1 pound boxes of salt would they need? Something that you do need to know, right? 1 pound is 453.6 grams. Yeah. All right, so take a moment there and see what you come up with. Okay, so let's take a look. So in this particular case, we are given 150 cubic centimeters. So remember, that is a volume when we see cubic centimeters. We are given the density here, which is 2.16 grams per cubic centimeters. And we want to know basically, how many 1 pound boxes can we sort of buy or need to buy. So if you're not really sure where you should go with this, obviously density is involved. So if we think about density, which is mass divided by volume, clearly here we do have the density and we do have the volume. So mass would seem like a logical approach as to maybe where you should go next. Once you get the mass, which would be grams, you could then maybe determine, how many pounds you might need in terms of boxes. So one thing that we can do is if we are given the density, we could use the density as a conversion factor. So we could think of density and really use it as a conversion factor. And in this particular problem, we can take a dimensional analysis approach to it. And we could actually start with our 150 cubic centimeters. And again, taking that dimensional analysis approach, I want cubic centimeters to be in the opposite location. So I would use it like this. And I do know, again, I'm going to be multiplying the top and dividing the bottom. And in this case, that will cancel out my cubic centimeters and give me 150 times 2.16. Can give me about 324 grams of salt that's needed. In terms of significant figures, if we were going to give that as our answer, that has 2. This guy has 3, which means perhaps 320 grams of salt if this was, again, going to be our answer for significant figure-wise. By the way, one of the benefits, as you can maybe see here in terms of taking a dimensional analysis approach, is I did not have to worry about rearranging this equation because the dimensional analysis did the math for me. Because I set it up getting rid of the units, I know math-wise I multiply and divide. I don't have to worry about did I rearrange this equation correctly. So again, a benefit of dimensional analysis is sometimes you don't even necessarily have to think about the actual formula, rearrange the formula. All you have to remember is multiply the top, divide the bottom. If you set it up where the units cancel out correctly, you pretty much rearrange the formula without even having to thinking about the formula. So sometimes it's very helpful in that sense. We do want to make sure that we do answer the question. So clearly 320 grams is less than 453 grams. So really one box, right, is all we would need. We'd have some left over for our fries later to put on that. Yeah. So any questions on that there? Questions on density or anything like that? All right, so that's going to actually wrap up chapter 2.